Translational kinetic energy, or TKE, is the energy that is contained within an object due to its mass and its motion. And so we have a formula for calculating what the amount of energy that particular mass is carrying at a particular speed. We see that here. So the energy is equal to 1/2 times the mass of the object times the square of the velocity. And then, as always, take note that we've got g sub c in this equation. So if we're operating in SI units, or if our mass is in the slug system, g sub c is going to equal 1. But if we're in engineering English, we of course need to use our value of 32.2. So the units for energy, as it is for kinetic energy, as it is for all energy, is joules. So that's Newton meters. And so if we look at the formula there, we're going to have a mass in kilograms. We're going to have a velocity squared, so that's going to be meters per second with both of those squared. So newtons are kilogram meters per second squared. So we have an extra meters in there, so Newton meters confirms for us our correct units, joules. So in the example that we have below, we're trying to find the kinetic energy of a car that's traveling at a speed of 65 miles per hour. So we're asked for the answer in SI units, so we're going to have to do a little dimensional analysis as we go through this. But fortunately for us, g sub c is going to equal 1. So I've got my 1/2, I've got my 1,000 kilograms, and then we have our 65 miles per hour, and that's going to be squared. So that means all of our conversion factors are going to have to be squared as well. So if I want to convert those hours into seconds, I'm going to need 1 hour over 3,600 seconds squared, and then I need to convert those miles to meters. So hopefully at this point we've committed to memory that it's 1 mile is 1,609 meters. And again, that's going to be squared. So with everything here that we see, we're going to just multiply it all out and then end up with an answer to 3 significant figures. And so when we're all said and done, we get an answer of 4.23 times 10 to the 5th joules. Now that's 423,000 joules. So we could also write our answer as 423 kilojoules. So we have the option in either case of writing it in kilojoules or joules. Just depends on what is asked of us in a given problem. The work energy theorem states that the work done by a force on an object doesn't disappear, it just gets transformed into kinetic energy. And so essentially what we have here is the work that's done on an object is going to be the change in the kinetic energy of the object. And so that's going to be our 1/2 times the mass times the difference of the squares of the velocities. And so if we apply that to the question that we have in front of us here, we have a 145-gram baseball is thrown with a velocity of 25 meters per second. And so we want to know, first off, what is its kinetic energy? And then we want to know what's the work done on the ball to make it reach this speed if it started from rest. So let's start with that kinetic energy. So our TKE of the object at its 25 meter per second velocity is going to be 1/2 times the mass, of course, needs to be in kilograms, so 0.145 kilograms times our velocity at 25 meters per second. And then we need to square that. So if we crunch that out on our calculator, we'll end up with 45.3 joules, rounding off to 3 significant figures. And so then the question is, what's the work done on the ball to make it reach this speed? Well, if we look at our work energy theorem up above, our 25 meters per second is going to be the final velocity, and then our initial velocity would be 0. So the amount of work that's being done on the baseball is equivalent to the kinetic energy that the ball has once it reaches that peak speed. So our work in this case will be 45.3 joules. Obviously, if that initial speed was something other than 0, then we would have to do a new calculation. And that's exactly what we see in our last example. So we see our car now has a little bit more mass at 1,250 kilograms, and so we're going to see how much work is required to accelerate that car from 20 meters per second to 30 meters per second. So we can go to that work energy theorem to find what that change in the TKE is, which is going to be the amount of work that's being done. And so again, we're in SI units, so we can ignore the G sub C. So we've got 1/2 times the mass, 1,250 kilograms. And then it's going to be the difference of the squares of the velocities. So the final velocity is that 30 meters per second squared, and then I'm going to subtract that 20 meters per second, and then that needs to be squared as well. And so again, this is just a lot of arithmetic here that we're going to have to navigate our way through. So we've got the 1/2 times the 1,250. Now in here we're ending up with 30 squared, which is going to give us 900, and that's going to have 3 significant figures: meters squared per second squared minus 400. So we've got 400 meters squared per second squared. So if we subtract those, we end up with 1,250 times 500 meters squared per second squared. And so we've maintained our 3 significant figures throughout that entire calculation. So now we're going to multiply that times the 1,250 and times the 1/2. And so we eventually end up at 313,000 joules. We could write that in scientific notation if we wanted to, but we do reflect the 3 sig figs there. And then again, we could divide that by 1,000 and then end up at 313 kilojoules. So again, we just need to pay attention to what our final unit request is. If one isn't given, then either of these 2 answers would be sufficient.